did you all think? Or is that not a good question for me to ask? Okay. Is it okay? Okay. So, I decided to throw that together about 15 minutes before class started. And so what I'll do for each question that you get right, because there were 5 questions, it'll be worth 0.4 points. Okay. So 0.4 points. So if you get all 5 correct, that's 2 points. So I will add 2 points to your final exam grade. So when you take your final exam, you can have a max of a 2-point bonus added to that grade. Okay. Sound all right? Okay. So that's what that's going to be for. All righty. So you all ready to talk about imaging detectors? Yeah. Okay. When it comes to imaging detectors, there's just there's a lot of terminology, a lot of parts, a lot of components that you basically just have to memorize. There's no way around it. So, this is a little different from talking about like interactions in matter. Like interactions in matter and talking about contrast and receptor exposure, you really do have to know how the process works. When it comes to the image detectors, it's a bulk of it is just knowing the components that make up the different detectors and the purpose that these different components serve. So it's something that if you wait until the last minute to look at it, all of these components will get jumbled in your head. So you need to take some time, even if it's just 10 minutes a day, and just look at these components so that you can start to learn them, so that when you take your next test, it won't be a struggle for you. You'll know what these components are and the function, or how they work. Okay. So we're going to look at a variety of detectors. Let's see if I can find my PowerPoint here. And show. Okay. Are you all able to see that? Okay. Let me get you all to where I can see your smiling faces. Okay. I know everyone's glad it's Friday. Only a month left. Ooh. All right, so I'm going to look at imaging systems, and I've got to think about 60 slides, something like that. We'll see how far we get today, but then we'll finish it up the Monday that you all get back. Okay, so really we only have 3 topics left. We have imaging detectors and image processing and fluoroscopy. So that's it. Those are the last 3 topics. And then you've got a majority of the information. There are some additional things that we'll talk about fall of next year, but by and large, you'll have all of the imaging information that you need. So, we've covered a lot between the summer and this semester. All right, so with digital detectors, we're going to look at the composition of them. And we'll also look at acquisition, meaning how they acquire the images, looking at how these components work to get that image. And then we'll take a little look at image extraction, which means how does this detector release its image data? And then we'll talk a little bit about data conversion. All right, so with digital detectors, the function of a digital detector is to capture the remnant beam. Now, you all remember, where is the remnant beam coming from? I can't get more simplistic than this type of question. Where's that remnant beam coming from?
The tube.
The patient. And by the way, the remnant beam consists of what 2 things? What 2 things make up the remnant beam?
Transmitted and scattered.
Yeah. Exactly. Transmitted photons and scattered photons. That's our remnant beam. Well, when we look at our detectors, we can classify them into these 2 different types of detectors, cassette-based or cassetteless. So the one that we use down in the lab, would that be classified as cassette-based or cassetteless? Oh, you all should
Cassette
be.
based?
It's cassette-based, yeah. It's a cassette. That image receptor is a cassette. So when it comes to cassette-based types of detectors, we have some different kinds. We have a photostimulable phosphor plate, which is a PSP plate. There are flat panel detectors. You may also hear them referred to as a thin film transistor, but most people use the terminology flat panel detector. That's like the one that sits in the battery charger on the counter in the X-ray room 1. And then we also have a PSP plate with a charge coupled device. So we kind of have like a hybrid detector. So those three are examples of cassette-based detectors. For cassetteless, you'll see that there are some things in common here. With cassetteless, we also have a flat panel detector. There's also a charge coupled device. There is a CMOS or complementary metal oxide semiconductor. And then there's also a PSP plate that is used in conjunction with a CCD. So it's a hybrid detector, but it's cassetteless. So you'll see that there's some similarities there, in terms of having a flat panel detector that can be cassette-based and cassetteless, and then having this hybrid detector, which is the PSP plate with a charged coupled device. It can be cassette-based or cassetteless. There are some other types of imaging technologies that we'll talk about next fall. These are more of the so-called, traditional detectors, so to speak, although they're extremely common. This is what most facilities use, but there are some new technologies out there, and so I'll share those with you next fall. So just, as a look here to see what these things look like, examples of cassette-based, this is what we have down in the lab by Fuji. They're cassettes. When you look over here, this is by Carestream, and that is a flat panel detector, but it's a cassette. Okay, it's a cassette. And then AGFA, now I don't have a picture of the cassette, but the cassette would look very similar, to one of these cassettes here. But this is the processing device. So the cassette is actually a PSP cassette or PSP plate. So, it would have a PSP plate in it like this one does. But when you insert it into this device, there is a CCD, a charge coupled device, that will scan the image, and we'll talk about that. So it's a hybrid, because a CCD can be used by itself, or a CCD detector can be used in conjunction with a PSP plate. So we'll talk about that one as well. We won't get to that one today. We'll end up talking about that on the Monday when you all return. But anyway, that's just a hybrid technology. So you have a PSP cassette, and then in here, there's a CCD type of scanning mechanism. And then for cassetteless, these are a couple examples here with Konica and DXRAD. With Konica, this is a flat panel detector that is in here, and with DXRAD, in here, it's a CCD detector. So these are cassetteless. Why are they called cassetteless? What's the difference here? What do you notice?
Isn't like the image detector already built in?
I'm sorry, I couldn't hear you, Sierra. I'm sorry.
You don't have to process the image.
You don't have to process the image. You don't have to process the image. That could be one thing. Now, with some of the flat panel cassettes, though, you still don't have to process it. You don't have to move it. So that's true to a certain extent. As soon as the image is received by this detector, it will start processing. But that is also true of this type of detector here. Okay. But yes, that can be true with these. The main thing is, if you look, it is built into the equipment. There's not a cassette. The detector is built into the equipment. When you have these cassettes like this, they're not built into the equipment. You have to take that cassette and you have to place it either on the tabletop to use it, or you have to put it in the bucket. But when you have a cassetteless unit, it is incorporated into the equipment. So when we first converted to digital imaging, what type of detector do you think was first on the market? Cassette-based or cassetteless?
Cassette-based.
I'm sorry, what? Somebody said something, but I couldn't hear it.
The cassette-based.
The cassette-based was actually first on the market. The reason for that is because all you had to do to convert to digital was get rid of your screen film cassettes, get rid of your chemical processor, purchase these cassettes here with phosphor plates in them, because these were first on the market before this one over here. So purchase these cassettes and get the reader device, just like we have down in our lab. So that was the most economical way for a facility to convert to digital. And plus it was first on the market. Even when these devices came out, a lot of facilities, when they converted to digital, they would use the Fuji cassettes like we had, just because it was a lot more economical than actually purchasing this equipment. Because in order to get this, you'd have to rip out your entire x-ray room and actually bring in new equipment. So it was a lot more expensive. Now, of course, the prices have come down, and some facilities will opt to go ahead and get this because the prices have come down. But just so you kind of know how that conversion took place. These are also examples of cassetteless. This is a mammography unit, and this happens to be the detector right here. And inside of that protective covering, it's a CMOS detector. And then in this cassetteless unit here, and they used to have this one. This was an image that was actually taken over at UNC Hospital, so they had it in a room there. It was called the Fuji Velocity, and this is one of those hybrid technologies where this one has a PSP plate built into it, but it also has a CCD built into it. So this is a hybrid technology. So they used to have that over at UNC. Okay.
It makes me think of when computers went from like CPU and monitor to like laptop,
Exactly. And even before that, when the computer used to take up the whole wall in a room, and individuals would have to use punch cards for computers. Did y'all ever learn about any of that? Not how to do it, but I didn't, if any of you had taken a computer course and had learned any of that information.
I've heard about it, but never
heard about it.
Yeah.
Has anybody watched the movie? This is one of my favorite movies, Hidden Figures. Phenomenal movie. They have those computers in there that were like punch card type of computers, and you see how much space those computers take up. And so, yeah, exactly, Casey. Now we're down to, laptops, down to tablets. I mean, even our smartphones. Yep, exactly. So it really is amazing. That technology really is amazing. Okay. All right. So some of the terminology that you need to know in terms of how the detector forms the image or captures the image. We have direct versus indirect. So in other words, we can categorize our detectors according to how they handle the image data. So if we have image detectors that are referred to as direct, what that means is that detector will take those X-rays and convert them directly to electrons. And the only one that we have that's classified as a direct type of detector is the flat panel detector, but it's called a direct flat panel detector. We'll take a look at this so you'll better understand it. Indirect, if we have an indirect detector, what that means is when the X-rays enter the detector, they don't get converted to electrons immediately. The X-rays will actually get converted to light first, and then they get converted to electrons. So X-rays get converted to light, and then the light gets converted to electrons. And the way you can remember this, the way I remember it, indirect has eyes in it, light has an eye in it. So if we have an indirect detector, that means we're going to end up with light somewhere in that process. So X-rays get converted to light, and then light gets converted to electrons.
That's funny to me.
So PSP plates are considered to be indirect. We have a flat panel detector that is classified as an indirect type of flat panel detector. CCDs, CMOS, those are indirect types of detectors. And then our hybrid detector, the PSP CCD, is also classified as an indirect detector. Remember when we talked about signal to noise ratio? The signal is, of course, the noise is the bad information, useless information, but the signal is our image data. The signal is referring to the electrons, because X-rays end up getting converted into electrons, and it's those electrons that are referred to as a signal. That's our image data. So our X-rays get converted into electrons, and that's the signal. That's the signal that the detector has. Okay. You okay so far? Okay. All right, so let's start with the PSP plate. So PSP plate is a type of indirect detector. And you've seen this image before. Took the PSP plate out of the cassette down in the lab, took a picture of it. There's a protective coating on it, of course, so you can't actually see the phosphor crystals, but that's what the plate looks like. Now, the PSP plate itself will capture the X-rays, and the X-rays will actually get converted to electrons, okay? But you need to hold on, because, I've just said it's an indirect detector, okay? So the PSP plate, when it receives the X-rays, we end up with electrons being trapped, and we'll look at this process in a moment. Then what happens is you take that cassette and you put that cassette in the plate reader. So you put it in that reader device, and when that plate comes out of the reader, the electrons will end up being released, and they will get converted into light, and then the light gets converted into an electronic signal. So because we have light in the process, this is referred to as an indirect detector. But notice that X-rays do get converted to electrons first, but then those electrons get converted into light, and then the light gets converted back into electrons or an electronic signal. So overall, this is still classified as an indirect detector, because we do start out with X-rays, we have light somewhere in the process, and then ultimately we do end up with electrons or an electronic signal. Electronic signal is just another name for electrons. Okay. So in terms of the composition and the acquisition, there is a protective layer. So what you're looking at is like if we were to take a cross section of that phosphor plate. Now, of course, that phosphor plate is really, really thin. So, it's magnified here for you to appreciate it. But this is the protective coating. So that white layer that you saw in the previous slide, that's the protective coating. The active layer is this layer here, and those are the phosphor crystals. The phosphors are made of barium fluorohalide, and this is, you have to know, you're just going to have to know this, there's just no way around it. So these phosphor crystals are made of barium fluorohalide, and there is europium added to the phosphor crystals as well. So there's barium fluorohalide, and europium is added to it. Sometimes the way people will say it is they'll say that the phosphor crystals are barium fluorohalide and it's doped with europium. That just means europium is added to the mixture. Okay. So what does that barium fluorohalide do? It will absorb the X-rays, and then those crystals will convert the X-rays to electrons, and those crystals will also store the electrons. So those crystals do those three things: converts X-rays to electrons, well, first absorbs the X-rays, converts the X-rays to electrons, and then it will store those electrons. It has to store them because we have to take that cassette and it has to be processed. Then there's also a support layer here. It's just a base. It's flexible though. It's not, this plate is not rigid. It does have to have flexibility because when it goes into the reader device, it will go through a roller assembly. There are rollers that move it through the various segments in the reader device, and we'll take a look at those segments. So it has to be flexible. It has to be flexible. It is not a rigid plate by any means. Okay. All right. So what you're looking at here is just a very simplified illustration of what takes place in the PSP plate. Okay. An X-ray will come in and it will interact with the barium fluorohalide crystal. So there are crystals in here. And, X-rays, when they interact with atoms, they can release electrons, right? Isn't that ionization? Yeah. So the X-ray is causing the barium fluorohalide atoms to be ionized. It's releasing electrons from the barium fluorohalide. And any time energy gets imparted to electrons, they get excited. Like when we talked about Compton and photoelectric, when an X-ray interacted with an electron, didn't that electron get ejected from the atom? And it'll have a certain amount of energy. The X-ray gives up a certain amount of energy, to electrons. So we're not going to go into a chemistry discussion about valence band and conduction bands. But essentially what the conduction band means is it just means it's the elevated energy state in the atom. So it's created when these electrons are knocked out of orbit. They're energized, so they have an energy state. But the thing is, when the atom is ionized, we don't want that electron to be lost and just go off into the nether regions. Like with Compton and photoelectric interactions that take place in the patient's body, when electrons are knocked out, like with Compton, if an electron's knocked out of orbit, that electron can go on to other atoms and interact with those atoms and settle into vacant shells. We don't want that to happen with these atoms that have been released by the barium fluorohalide. We want them to stay in the vicinity of the atom from which it got ejected. Okay. So there is europium that is added into those phosphor crystals to create these energy traps. So these energy traps will trap these electrons, and it will prevent these electrons from either settling back into position with the atom that it was ejected from, and it also prevents it from settling into the atom next door if there's a vacancy. So essentially these traps they're keeping the electrons, they're keeping the electrons from going back and joining back with the atoms. The reason we want that to happen is because this is our image data. And if we lose these electrons, if they drop back and recombine with the barium fluorohalide, we lose our image data. Oh, look at the dog. So then we lose that, okay? So you need to know that europium creates energy traps in the phosphor crystals. So this is our image data. That's our image data. Are you okay up to this point? X-rays come in, they ionize the barium fluorohalide phosphor crystal. So those electrons are released. Europium is going to trap those electrons, and it's going to hold on to our image data. Okay? then, our plate, it's holding that image data. We have to have some way to get that data out of there. So what happens is the image extraction process, we will take that plate and, like, for example, go to the reader device. The plate is removed. There's a laser in there that will scan the plate. The electrons will be released from the europium. Light will be emitted. There's a light guide device that we'll talk about that will gather that light, and light will be directed to a photomultiplier tube where ultimately we end up with electrons again. So this is essentially the chain that is taking place for this image extraction. So
What did you say? Sorry, what did you say PMT was?
Photomultiplier tube, and you'll see, because we're going to talk about all of those. I just want to show you kind of the overall picture of what's happening, and we'll get to that, but it's called a photomultiplier tube. So these are just some different examples of readers. You should recognize this one here because that's like the one we have in our lab. It's called a multi-plate reader. You can stick up to four cassettes in that one. This one here is just a single plate reader. It'd be used at a small clinic, small doctor's office. This particular plate reader here just has one slot, but it has a workstation connected directly to it, which is kind of nice. And then this one over here, this one happens to be by Carestream, which used to be Kodak. And with this one, you can put in multiple plates. You can put in more than what you can with this Fuji reader, but you notice that they happen to be placed upright here. And then when it's kind of like a little conveyor belt thing. And when they get to the end of the conveyor belt, they go down, they'll kind of get sucked down into this reader device, the plate will. But anyway, it's just a different setup. And here you've got a workstation attached directly to it. Because Kodak or Carestream, they also made phosphor plates, just like Fuji. It's just, different way of doing it. Every vendor was a little different. So when you look at a reader, so for example, if we were to take the side off of our reader, this is kind of what it looks like. So our cassette goes in, and then the device will open up the latches. So that's why you have to stick it in, with the latches going in first. So the latches will open up, and that imaging plate is extracted, is taken out, and it's sent through these roller devices. Won't deal with this erasure part right here because we don't want our data to be erased yet. So it comes past here, and it goes down here to this. This is our area of interest right now. So it goes down to the bottom of the reader, and there's a mirror in there. There are optics, which is a laser, and then there's this light collection device and a photomultiplier tube. So there's this whole system, this all these different components down here in the bottom of the reader that will extract this image. So we'll go through these pieces, but I just kind of wanted you to see, what a little graphic representation would look like. So down in the bottom part of that reader, we've got this thing called the scanning assembly. I know in this, here it's only pointing to the light collecting system, but this whole thing through here is what the scanning system is, this optics and the mirror. So it's the biggest part of the image collection system, or image extraction system rather. Okay. Oh, let's see, 10:50. You know what, how about,
No, just keep going.
why don't we take a break since it's about 10:50? You want to do that?
Not really.
We come back at I was about to say 10 o'clock. My times are messed up. 11 o'clock? Okay, let's do that before we finish this up. So I'll see you in 10.